Every year worldwide, over 200 million miles of steel wire are produced. That's enough to wrap around the Earth more than 8 times. But few people imagine how this silvery vein of strength is born, the one that holds up bridges, elevators, cranes, and even underwater cables. Its path is a trial by fire, acid, pressure, and time. How do you turn 10 tons of rough metal into a thin, shining thread capable of withstanding hundreds of tons of load? In this video, we're going to dive into the most secret workshops where steel becomes the muscle of civilization. And we guarantee you won't be able to tear yourself away. To create a steel cable capable of holding up a bridge hundreds of feet long, it all starts with the right alloy. Most often, it's carbon steel, with a carbon content of around 0.6%, which provides both strength and elasticity. Sometimes chromium, nickel, or molybdenum are added for corrosion resistance and increased load capacity, especially for cables that need to work outdoors for decades. The metal is delivered to the factory in the form of huge steel slabs, plates 10 by 2 by half a foot in size and weighing up to 10 tons. They are heated in furnaces to 2,200 degrees Fahrenheit until the steel becomes malleable, almost like rubber. Then these red-hot billets are passed through rolling mills, turning them into long, thin rods with a diameter of approximately 0.25 inches. These are called wire rods. These wire rods are then cooled under controlled conditions, either in air or in special baths, so that the metal structure is dense and the internal stress is uniform. Next, a short storage stage. The metal is weighed, checked for hardness, flexibility, and the presence of microcracks. Only after this is each coil sent to the main section, wire drawing, from which the future cables will be formed. After the steel wire rods have been cooled and checked for quality, they proceed to the wire drawing workshop. This process transforms the thick rods into thin but incredibly strong wire, which will become the foundation for bridge cables. Imagine a steel rod as thick as your finger, just off the billet. Its surface is rough, as if covered in a layer of sand or rust. This is scale, a hard and brittle crust that appears during hot rolling. To prevent it from interfering with further metal processing, it needs to be removed. To do this, the wire rod is first lowered into a bath of acid solution, usually sulfuric or hydrochloric acid. In this solution, the scale seems to flake off the metal, just like old paint peels off after being treated with solvent. Then the wire is rinsed with a large amount of water under pressure to wash away all traces of acid and dirt. To the touch after this, the metal becomes smooth and cool, like a freshly polished stone. But that's not enough. Next, the wire goes through degreasing. It's submerged in special alkaline solutions that remove any oils that might have gotten onto the surface. And only then is the clean, smooth wire, shiny and dry, ready for the next stage, drawing. Now, the wire needs to be pulled through a hole, smaller than the wire itself, to stretch it out and make it thinner. But a thick end simply won't fit through. So, it's first sharpened. This process is called pointing. The wire is fixed in a special mechanism that resembles strong metal vice jaws. One end of it is inserted into a device similar to a small press or crusher, where the steel casing is gradually squeezed and stretched into a cone shape. This way, the wire is essentially machined into a pointed tip. Imagine a pencil sharpened at one end, only it's not graphite but cold, shiny metal. This sharpened end then easily fits into the first opening of the drawing machine, a small metal die. To the touch, such a sharpened part becomes thin, like a shoelace, but remains elastic and strong. This is where the drawing process begins, which will turn the rough wire rod into a thin steel wire for the cable. Picture a shining metal strand, about the thickness of a pencil, being gradually pulled through a series of metal rings. Each of these rings is a drawing die, looking like a coin with a hole in the middle, but made of super hard material, like tungsten carbide. The holes in each die are slightly smaller than the previous ones. The whole system is arranged in a line, like beads on a thread. The wire passes through the first ring, and it compresses it, stretches it, reducing its diameter. Next, the following ring, even smaller, and the same thing happens again. The entire wire is pulled by a powerful drawing machine resembling giant toothed rollers or high traction rollers. It constantly pulls the wire forward, maintaining tension and thus forcing it to pass through the dies. To the touch, after several passes, the wire becomes thinner and longer, like a silvery strand of hair. The surface is smooth, cool, with a clear metallic sheen. Importantly, this entire process happens without heating. The metal remains cold. That's why it's called cold drawing. The steel gets stronger in the process. Its structure becomes denser and more durable, like a muscle that's been trained. And so, ring after ring, an ordinary wire rod transforms into a high-precision wire for a future steel cable. The steel thread that has just passed through a series of drawing dies has become thinner and stronger, but at the same time, stressed, like a stretched string, with fatigue hidden inside. The metal has accumulated internal stresses, microscopic defects that reduce its ability to bend or stretch further without cracking. Yes, this wire has become brittle. To release this stress, the wire passes through a special thermal furnace. It's not visible from the outside. It's a long metal tunnel structure, inside which the temperature reaches over 1,000 degrees Fahrenheit. In such heat, resembling the middle of a bonfire, the wire slowly moves through the furnace, either lying on moving rollers or suspended. It gradually heats up to the required temperature and then slowly cools down. The whole process takes anywhere from a few minutes to an hour, depending on the thickness and grade of the steel. To the touch, the wire after this stage is just as smooth and shiny, but it no longer breaks. Inside the metal, its crystalline structure has rearranged itself. The stresses are relieved, plasticity is restored. Now it's ready for the next series of drawings, and it will become even thinner, stronger, and more durable. It's like giving muscles time to recover before a new workout. In the final stage, the wire undergoes a final quality control, and this is definitely not a simple visual check. A long, almost continuous strand of shiny metal moves at a speed of tens of feet per second through the inspection unit. There, it's met by special sensors. This could be laser equipment that non-contact measures the wire's diameter with an accuracy of thousandths of an inch. Nearby, devices that determine strength. A portion of the batch is selected for mechanical testing. The wire is clamped in hydraulic jaws and pulled until it breaks. This determines its tensile strength and breaking load. If the wire holds up, it's ready for work at heights of hundreds of feet, supporting the weight of a car bridge. The surface is checked separately for microcracks, burrs, corrosion. High-resolution cameras or even eddy current testing are used here, which can see beneath the top layer of metal. And only the wire that has passed all these tests gets the green light. It will become part of a steel cable, capable of withstanding years of loads and harsh weather. This is the final touch that guarantees what arrives at the construction site is reliable, like steel itself. After inspection, the quality wire is neatly wound onto large spools. The wire passes through guide rollers and tensioning mechanisms that ensure the coils lie tightly, but not too tightly. All this happens on high-speed winding machines. Spools come in different sizes. For thin wire, they might weigh hundreds of pounds. For thicker wire, a ton or more. Then these spools head to the next stage, the actual twisting into cables. But even before this, they are sometimes coated with an anti-corrosive compound or lubricant so the wire isn't damaged during storage and transport. Spools of wire are usually moved using forklifts, cranes, or special carts because the weight of even one spool can reach several hundred pounds or more. Manual labor is ruled out here. Otherwise, the risk of injury would be too high. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is FIAES, stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Karblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, The disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length. A groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a 45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection. By eye, through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to negative 260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create 3 separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. And 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about -260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Did you know that each year the world builds structures so massive, skyscrapers scraping the sky, bridges spanning vast canyons, ships larger than city blocks, that they require metal parts shaped with forces equivalent to thousands of tons and precision measured in mere millimeters? This isn't just cutting and welding metal in a workshop. This is bending steel plates thicker than your arm, forging colossal parts under unimaginable pressure, and machining giant structures with surgical accuracy. Get ready to witness the most impressive, largest-scale metal fabrication methods on Earth, uncovering the hidden power and precision that builds our modern world. The sheer scale of metal fabrication hits you right away on the factory floor. We're talking about moving and shaping pieces that weigh tons. One of the most fundamental and visually impressive processes is metal bending. Forget bending a paperclip. Imagine bending steel beams strong enough to support a building, or curving thick metal plates for ships and pressure vessels. Massive machines called press brakes or roll benders use incredible hydraulic force to shape metal. Picture a giant press pushing down with thousands of tons of pressure to put a precise bend in a steel beam, or colossal rollers curving a thick steel plate into a perfect cylinder. These aren't just big tools. They're feats of engineering designed to apply immense force with fine control. On the biggest scale, you see specialized machines like the FKB 3-roll plate bending machine, capable of shaping massive steel plates for tanks, wind turbines, or ship hulls with incredible accuracy. Software like Bentronic controls the rollers with millimeter precision, even on pieces the size of a room. Another impressive example is bending giant steel beams for structures. Machines like the Faction R CMI use powerful hydraulic rolls and guide systems to curve huge I-beams or H-beams into exact shapes needed for complex architecture or bridges. Applying that much force while maintaining the beam's structural integrity is a true industrial art form, making metal flow like clay, but under thousands of tons of pressure. Another mind-blowing method is metal forging. This is using localized compressive forces, often with immense power and heat, to shape metal. Think of a blacksmith, but on a scale where the hammer is a machine delivering thousands of tons of force. In massive forging presses, heated metal billets, solid blocks of steel, are pounded or squeezed into complex shapes. This process changes the metal's grain structure, making the finished part incredibly strong and durable. This is how critical components for aircraft landing gear, engine parts, or even massive artillery barrels are made. At places like the Waterlet Arsenal, you see iconic machines like the rotary forge. This is a different kind of forging, using rotating dies to hammer and shape a heated steel billet into a hollow tube, like a cannon barrel, with incredible speed and precision. These machines have been operating for decades, playing a vital role in producing thousands of heavy-duty barrels for military systems. The sheer force and rhythmic pounding of these colossal machines working on red-hot metal is one of the most dramatic spectacles in metal fabrication. showcasing raw power precisely controlled. Once metal parts are formed by bending or forging, they often need precision finishing. This is where machining comes in, using tools to cut away material and achieve exact dimensions and shapes. On the bigger scale, this involves massive CNC, computer numerical control, machining centers working on parts that weigh many tons. Imagine a machine tool the size of a small house, precisely cutting, drilling, or milling a giant metal casting or forging with micron-level accuracy. Sophisticated software controls these machines, making complex cuts and achieving tolerances required for critical components in aerospace, heavy machinery, or energy production. Precision machining isn't just about size, it's about achieving incredible accuracy on massive objects. Machines use advanced cutting tools made of hardened materials, sometimes cooled with high-pressure coolant, to cut through tough alloys. On critical components like gearbox housings, turbine shafts, or large crane parts, surfaces must be machined to tolerances that ensure perfect fit and smooth operation under immense loads for decades. It's a process where technology allows engineers to sculpt giants with the precision of a jeweler. Beyond these core methods, metal fabrication involves a host of other impressive processes on industrial lines. Cutting is a crucial first step, using powerful lasers, plasma torches, or water jets to slice through thick metal plates with incredible speed and clean edges. Welding is joining metal pieces together, from automated robotic welding arms building vehicle frames or ship sections, to skilled human welders performing critical structural welds that must withstand massive forces. Surface treatment like sandblasting and industrial painting or coating lines protect the metal from corrosion and give it its final look. Throughout all these stages, from the arrival of raw metal plates and beams to the final finished and assembled components, rigorous quality control is paramount. Industrial scanners, ultrasonic testing, X-rays, and precise measurement systems check every weld, every dimension, every material property. Experienced technicians and engineers oversee automated inspection systems and perform manual checks on critical points. A blend of high-tech monitoring and human expertise, ensuring that these massive metal parts meet the highest standards of strength, precision, and safety required to build skyscrapers, planes, and infrastructure. These massive metal fabrication facilities are not just factories. They are cathedrals of engineering power and precision. They process hundreds of thousands of tons of metal each year, shaping it into the backbone of our cities, transportation, and industries. It's a testament to human ingenuity and technological advancement, taking raw materials and applying immense force and incredible accuracy to build the physical world around us. It's a hidden, necessary industry that few people ever see. So, the next time you look up at a skyscraper, cross a bridge, or see a large machine at work, remember the mind-blowing industrial process that created its metal bones. The bending of giant beams, the forging of colossal parts, the precision machining of massive structures. It's all part of the amazing world of metal fabrication. It's a fascinating look into the power and precision that builds our modern world. What part of these impressive metalworking methods surprised you the most? Let us know in the comments. Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. There are more than 5 trillion pieces of plastic floating in our oceans, and this number keeps growing every single day. Turning trash into something useful isn't just a creative idea, it's an absolute necessity. This approach not only reduces harm to nature, but also proves that even the worst garbage can have a second life. Imagine this, that waste could be turned into something as stylish as sneakers. Surprised? Well, let's dive into this fascinating journey together. First, you need to find the trash. Specialized organizations rely on advanced collection systems to do this. Hunting for ocean trash is an impressive and highly technical process, using cutting-edge tools designed to capture plastic. One of the most renowned organizations tackling this issue is the Ocean Cleanup. They deploy massive floating barriers that are strategically placed in ocean currents, where plastic waste tends to accumulate in large garbage patches, zones of concentrated trash. Here's how these traps work. Large floating structures equipped with nets or barrier walls move through the water, capturing plastic that drifts into their range. These systems are designed to catch plastic debris floating on the surface, as well as some submerged deeper in the water. Imagine enormous nets gliding smoothly through the ocean, sweeping up all kinds of waste in their path. Once the trap is full, it's hauled to a specialized vessel, where the collected plastic is unloaded. This is done using massive mechanical cranes or conveyor belt systems. The unloaded waste is then sorted and cleaned to prepare it for recycling. These technologies don't just clean up our oceans. They create opportunities to repurpose plastic into new products like textiles, sneakers, and even construction materials. The sight of machines pulling massive piles of trash from the water is both inspiring and a little shocking. Plastic of all shapes and sizes, bottles, bags, broken fragments, and even old toys is brought ashore for sorting. It's a stark reminder of the scale of the problem, but also a glimpse of the incredible potential for change. Once the trash is unloaded onto the ship, it's transported to the nearest port. On land, specialized facilities equipped with conveyor belts and robotic sorting systems take over the next stage of processing. Here, the waste is sorted, cleaned, and prepared for recycling. The process moves at an incredible pace. Robotic arms sort the plastic by type, like assembling a massive jigsaw puzzle. This isn't just random sorting. Advanced technology can detect even the tiniest pieces of plastic. After sorting, the trash gets washed. Much of it is covered in algae or other organic matter, so cleaning is a messy, but absolutely crucial step. Sorting is followed by a multi-step washing process. First, the waste is rinsed or scrubbed to remove large contaminants like sand or dirt. Mechanical systems, such as conveyor belts, move the trash through brushes or nets that scrape off big debris. Next, the smaller impurities like oil residues or fine dirt are removed. This can be done in several ways. For instance, as the trash moves along a conveyor belt, high-pressure sprayers rinse it with water. The jets dislodge grime, organic residues, and oil stains. Another method involves submerging the waste in water tanks. These tanks often feature circulating currents, which enhance the cleaning process by gently agitating the plastic and rinsing away remaining dirt. To tackle oil contamination, the plastic is treated with specialized cleaning solutions or chemicals that break down petroleum products and other stubborn pollutants. After these stages, the plastic is finally ready for recycling or disposal. The water used in the cleaning process typically undergoes filtration, so it can be reused or sent for purification to reduce environmental impact. This precise and efficient system ensures the waste is clean and ready for the next step, with adjustments made depending on the material type and its level of contamination. The process of shredding and melting cleaned ocean plastic is truly mesmerizing. A real choreography of technology where each step amazes with its scale and precision. Enormous machines, resembling giant blenders, slice, grind, and crush the plastic into tiny granules. These powerful devices, equipped with massive blades and cutting tools, work at incredible speeds, creating an artificial snow of microscopic plastic particles. As mentioned earlier, the scale of this operation is astonishing. These machines can shred over 1,000 pounds of plastic per hour. The shredded material is ground into granules, which are then sent for melting at temperatures around 500 degrees Fahrenheit. For context, this is the point at which most types of plastic begin to melt and become pliable for reshaping. The roar of massive grinding discs and the compressed sounds of mechanical force fill the air as the plastic is transformed into tiny granules that shoot through the air. Different types of plastic are blended and shredded into a uniform mass. This isn't just waste, it's raw material, ready to be turned into something new. While the granules vary in size, each one is precisely prepared for the next step, melting. These shredded particles are then sent into industrial furnaces for a dramatic transformation. The melting process is comparable to dough that starts off hard and crumbly, but becomes soft and elastic under heat. Gigantic furnaces, heated to extreme temperatures, melt the plastic into a thick, almost liquid state. This molten plastic flows through pipes, gleaming under factory lights like a fiery river coursing through the corridors. In that moment, everything around feels almost magically alive. The melting technology is much like what happens when chocolate or wax is melted into a liquid form. Plastic doesn't just soften, it becomes flexible and easy to shape. At this stage, it's ready to be molded into new items. This semi-liquid material, balanced between solid and fluid states, represents the start of something new, a material reborn to re-enter the cycle of life. As the molten plastic cools, it hardens and takes shape, transforming into products that become part of our everyday lives. This is one of the most captivating stages of recycling, where simple trash turns into something useful, once again finding its place in the world around us. Adidas, Parley for the Oceans, and other brands are already turning ocean plastic into stylish products. For example, making sneakers out of this plastic looks like something straight out of a futuristic lab. Liquid plastic is poured into molds, where it hardens to form the perfect sole. The upper part of the shoe is woven from recycled plastic threads, a kind of textile wizardry that transforms trash into a fashionable accessory. Here's a fun fact. Producing just one pair of sneakers can use up to 11 plastic bottles. These sneakers are not only stylish but also eco-friendly, utilizing materials that might have ended up polluting our oceans. On a large scale, recycling plastic helps reduce dependence on virgin resources. For instance, recycling 1 ton of plastic cuts carbon dioxide emissions by as much as 1.5 tons. One of the biggest names in sportswear even created jerseys for soccer teams, including Real Madrid, made from plastic retrieved from the ocean. Now, players are quite literally wearing the ocean during their matches. What about construction materials? This is another equally fascinating avenue. Plastic granules are mixed with sand or other materials to create durable panels for construction. Ever considered that your home could be partly built from recycled trash? This is becoming a reality, not only reducing the amount of plastic in our oceans, but also cutting carbon emissions in the construction industry. In New Zealand, plastic bottles are being turned into synthetic sand for building roads. This sand is significantly cheaper and more eco-friendly than traditional options. Here's a staggering statistic. Every minute, more than 2,000 plastic bottles enter our oceans and seas. Only about 9% of all plastic waste in the environment is properly recycled. The rest ends up in landfills or the ocean, leaving us with serious concerns about the planet's future. But there's good news. Recycling ocean plastic isn't just about helping nature. It's also a booming business. For example, one company specializing in ocean plastic recycling processes over 22 million pounds of plastic each year, transforming it into sportswear and accessories. In the fashion industry alone, more than 500 million plastic bottles are reused annually to create new products. Many companies are repurposing old fishing nets, which pollute the oceans, into sneaker soles. These fish catchers are now turning into eye catchers when you slip on these stylish kicks. Some companies even craft trendy chairs from ocean plastic, including discarded fishing nets. The irony? These nets used to catch fish, and now they sit in restaurants.